Hello, welcome to another module in this massive open online course. So, we are looking at vestigial sideband modulation, which is basically a form of upper sideband Vestigial sideband modulation in which the filter is non-ideal. And let us look at the properties of this non-ideal VSB filter. So, we are looking at the property of this VSB filter, and let us say this has impulse, this has spectrum HF, correct. This non-ideal VSB filter has spectrum HF, which, as we already said, it is a high pass filter, but it is not an ideal high pass filter. So, it has a finite transition band, correct. So, this is minus Fc, and this band, these two bands, these are your transition bands, correct, where it is rising from, where the impulse, where the response is lies between 0 and 1, that is rising from 0 to 1, that is known as the transition band, and this is a non-ideal high pass filter, correct. Non-ideal high pass filter at with cutoff frequency Fc. This is a let me just write it again clearly, this is a non-ideal high pass filter. As we already said, we prefer this non-ideal high pass filter. We prefer this because designing ideal high pass filters or implementing ideal high pass filters has a very high complexity, okay, require a large number of stages to implement the ideal high pass filter and so on, whereas this non-ideal high pass filter can be implemented with relatively lower complexity, alright. So, this is preferred in a practical implementation, okay. So, let us look at a schematic for vestigial sideband modulation, okay. So, we have our signal MT, which is as usual modulated with cosine 2 pi Fc t first, because remember we are using the frequency discrimination, okay, frequency discrimination technique, except that we are using non-ideal. So, it is modulated cosine 2 pi Fc t. So, let us write this over here, that is cosine 2 pi Fc t to generate MT cosine 2 pi Fc t, and that is passed through your linear time invariant system with impulse response Ht, or that is your non-ideal high pass filter. Impulse response Ht and spectrum HF, and this is basically the output. So, naturally the output here will be, this is basically your MT cosine 2 pi Fc t convolved with Ht, because your modulated signal MT cosine 2 pi Fc t is passing through the non-ideal high pass filter with impulse response Ht. Therefore, the output is MT cosine 2 pi Fc t convolved with the impulse response, okay. So, this is the convolution, okay. So, that should be clear, this is your convolution operation, okay, which in the frequency domain means, and then for the frequency response of this, of the output, frequency response of the output is that is the Fourier transform in the frequency domain is the Fourier transform of mt cosine 2 pi f c t with multiplication, because convolution in time domain this becomes your multiplication. Okay. So, that is also something that you are must be very familiar with at this point. So, this becomes a your simple product. Let us write product instead of multiplication. Okay. And now the Fourier transform of mt cosine 2 pi f c t, that is also something that we are very familiar with, that is half mf minus, that is Fourier transform mf shifted to fc and mf shifted to minus fc. So, the Fourier transform of mt cosine 2 pi f c t, this is equal to half mf minus fc plus half mf plus fc. So, the net Fourier spectrum of the output. So, spectrum of the output of the VSB modulated signal, that is spectrum of the VSB modulated signal is half mf minus fc plus half mf plus fc times hf. Okay. So, this is basically the spectrum, let us call this as xf. If we call this signal as xt here, the VSB modulated signal as xt, this is our VSB, vestigial sideband modulated. If xt is the vestigial sideband modulated signal, let us say it has spectrum xf, that is this xt has spectrum xf. So, output signal xt, VSB modulated signal xt, where xt has spectrum xf, and that xf is given by this, that xf is given by this, that is half mf minus fc plus half mf plus fc, that is the spectrum of mt cosine 2 pi fct multiplied by hf, which is the spectrum of the non-ideal high pass filter, okay, which has a transition band around fc. Okay. Now, at the receiver, consider demodulation at the receiver. We have your xt, which is the received signal. This is again demodulated by passing through, by demodulating with your cosine 2 pi fct, and that gives rise to the output signal. Okay, so, let us call this output signal as RT with spectrum, let us say RT is the output of demodulator that has spectrum RF. Okay. So, RT, this is the output of, this is the output of the demodulator. Okay. So, this is basically RT, and see RT is basically your xt times cosine 2 pi fct, and therefore, RT is basically demodulated xt times cosine 2 pi fct. Therefore, its spectrum is naturally half xf minus fc plus half xf plus fc. Okay. So, this, so xt cosine 2 pi fct, its spectrum is half xf minus fc plus half xf plus fc. Now substitute for xf. Now in this what we are going to do is substitute. So if we call this, this is the spectrum for xf, okay, spectrum of output, that is xf. So if we call this as equation 1, now what we are going to do is substitute for, that is equation 1 tells us that xf is half mf minus fc plus half mf plus fc into hf. Substitute that spectrum expression for the spectrum xf in this expression for the spectrum RT. Okay. So by the way, this is RF, that is a spectrum of output. Okay, this is the spectrum of output of spectrum of output of spectrum of the output of the demodulator, that is equal to half, okay, and instead of xf minus fc I am going to substitute that expression. So xf minus fc is, so we have half, xf minus fc is half mf minus 2 fc plus half mf mf. So this is half, so xf minus fc is half mf minus 2 fc, mf plus fc minus fc, that is half mf times hf minus fc. Okay, so this is your basically half xf minus fc plus half, now xf plus fc, that will be half mf minus fc plus fc. So half mf plus half mf plus fc plus fc, mf plus 2 fc into hf plus fc. Okay, so this is the net expression for. Now if you look at this, now let us write this term by term. So this is 1 by 4 mf minus 2 fc into hf minus fc plus 1 by 4 mf into hf minus fc plus 1 by 4 mf into hf plus fc plus 1 by 4 mf plus 2 fc into hf plus fc. Okay, see, these are the 4 terms that you get from the expansion of the output of the demodulator. So this is still, we are talking about the spectrum of the output signal of the demodulator, that is we are talking about the spectrum RF. Now if you look at this spectrum, which we have simplified by substituting the expression for the spectrum of xf, that is the spectrum of the xf, which is the spectrum of the VSB modulator signal xt. Now you can see that mf minus fc, look at these two, mf minus fc and mf plus 2 fc. So these two components correspond to 2 fc. Are centered at 2 fc. mf minus fc, mf minus 2 fc is mf shifted to 2 fc, and mf plus 2 fc is mf shifted to minus 2 fc. So these two are centered at 2 fc. So these can be eliminated by low pass filtering, hence these can be eliminated by low pass filtering. So when we eliminate these by low pass filtering, only the 2 other components are going to remain. So that is the central idea. So now we are going to low pass filter it. Now these can be eliminated by LPF, okay, that is your hence, now if we pass this through a low pass filter, pass RT through LPF. So, only these components are going to remain, that is 1 by 4 MF into HF minus FC, 1 by 4 MF into HF plus FC. So, once you pass this, you LPF and let us say you get R tilde F, that is output of LPF. So, here R tilde T is output of LPF, which is 1 by 4 MF into HF minus FC plus 1 by 4 into MF into HF plus FC. Okay. So, 1 by 4 MF into HF plus FC, and now if you take MF common, you can see this is 1 by 4 MF into HF minus FC plus HF plus FC. Now, therefore, if we can set this to a constant HF minus FC, so you can see the net output spectrum after low pass filtering is 1 by 4 MF into HF minus FC plus HF plus FC. Now, if you can set this HF minus FC plus HF plus FC equal to some constant, in particular let us say this is 1, then the output spectrum will be 1 by 4 MF, which is basically proportional to the spectrum of empty, that is in fact the output signal will be 1 by 4 empty. So, if this is equal to 1, then this is simply 1 by 4 MF, which in the time domain corresponds to 1 by 4 empty, and therefore, we would have recovered our, which implies that we have recovered our, implies that we have recovered our original signal empty. But note that the requirement is HF minus FC plus HF plus FC should be equal to 1. So, that is the property that the VSB filter, that the non-ideal VSB filter must satisfy. Okay. So, let us look at that property. So, we have HF minus FC. So, VSB filter must satisfy. So, the non-ideal VSB filter must satisfy for recovery, distortionless recovery, non-ideal VSB filter must satisfy the property HF minus FC plus HF plus FC equal to 1, non-ideal. This is the property that your non-ideal VSB filter must satisfy. Okay. So, let us look at this property that the non-ideal VSB filter must satisfy. So, this is your HF, correct, and or let us look at this. This is minus FC so this is your HF, okay. And now what we are going to do is HF minus FC is basically HF shifted by FC. So, HF minus FC is HF shifted, that is advanced by FC. So, we have HF minus FC. So, the band okay. So, this is basically your HF minus FC, and plus there will be some other component at 2 FC. We are not worried about that, alright. So, we are only worried about this component which is in the base band, that is HF minus FC. Now, let us look at HF plus FC. and if you look at HF plus FC, that looks something like this. So, this is your HF plus FC, that is basically your component that is at FC is shifted backward to the 0 frequency, that is HF plus FC, that is shifted by minus FC, that is shifted by FC to the left. Now, when you add these two, that is HF minus FC plus HF plus FC, the VSB filter should obey the property that VSB filter must satisfy the property that when you add these two, you get unity, that is you should get unity, that is HF minus FC plus HF plus FC equal to 1. So, this is the property that the VSB filter must satisfy. So, this is equal to 1. This is the property that the VSB filter must satisfy. And you can see this property is satisfied if the VSB filter is symmetric about FC. That is, if you can see, if this VSB filter is symmetric about FC, that is basically if this is symmetric about FC, that is this is let us say FC minus delta F, this point is let us say FC plus delta F, and then if it is symmetric about FC, then you can see that symmetric about FC in the sense that you can see that this is linearly increasing between FC minus delta F to FC plus delta F, the midpoint is at FC. So, if this is symmetric about FC, then this property is satisfied, or in other words, between FC minus delta F to FC plus delta F, this has to be HF equals 1 over, you can see this linear part corresponds to 1 over, the slope is 1 over, that is it is rising. So, this is 1, this is 0. So, slope is 1 over, it is rising to 1 in a interval of 2 delta F, 1 over 2 delta F times F minus FC plus delta F. So, if this property is satisfied, that is if this filter HF is symmetric about FC, that is starts from FC minus delta F to FC plus delta F and rises from 0 to 1 linearly, then you can see that when you shift HFC to, so when you consider HF plus FC and HF minus FC and superimpose them or add them in the base band, they will sum up to 1. So, the property that you can see, this is the property that the VSB filter must satisfy, HF minus FC plus HF plus FC equal to 1. One such filter has the response HF equals 1 over twice delta F in F minus FC plus delta F for FC minus delta F less than or equal to F less than or equal to FC plus delta F, and HF. So, HF equal to this equal to 0. So, for F less than or equal to FC minus delta F equal to 1, for F greater than or equal to FC plus delta. So, this is one particular filter, one particular VSB filter. So, this is one particular filter non-ideal, one particular ideal filter, non-ideal HPF, non-ideal HPF, which satisfies VSB property. Okay, this is one particular non-ideal high pass filter which satisfies the VSB property. All right. So, what we have seen in this module, what we have seen is basically we require, that is, one can implement a non-ideal version of single sideband modulation. All right. In this particular case, we have chosen upper sideband modulation, a non-ideal version of upper sideband modulation, which is termed as vestigial sideband modulation with a non-ideal high pass filter. All right. And we have shown if the high pass filter satisfies certain property, that is HF minus FC plus HF plus FC is equal to unity, then you can reconstruct, correct, you can reconstruct this VSB, you can reconstruct the transmitted message signal again empty without any distortion by again passing through the demodulator, that is demodulating with cosine 2 pi FCT at the receiver. However, the disadvantage of VSB modulation still remains that it requires a slightly larger bandwidth. In this particular case, you can see that the transition bandwidth is FC minus delta F to FC plus delta F. So, requires additional bandwidth of delta F, all right, which the previous upper sideband modulation scheme did not require. All right. So, require a slightly larger bandwidth, that is FM plus delta F, where FM is the maximum frequency. So, previously the upper sideband modulation required only FM, correct. Now, this requires FM plus FC, which is slightly larger than FM, but of course, it is a trade off. It allows for a lower complexity in the design of the non-ideal high pass filter. And if this non-ideal high pass filter satisfies this property HF minus FC plus HF plus FC equal to unity, then that allows the reconstruction of the message signal MT without any distortion by simply demodulating with cosine 2 pi FCT. Now, similar condition can also be derived for the vestigial sideband modulation with the lower sideband, that is non-ideal low pass filter, all right, and I will let you explore that, all right. So, we will stop this module here and continue with other aspects in the subsequent modules.